Hello, this will be a demonstration of proposition 35 from book 3 of Euclid's Elements, which says that if in a circle two straight lines cut one another, the rectangle contained by the segments of the one will equal the rectangle contained by the segments of the other. What this looks like is that we have some circle A, B, C, D, right? Like so. And we have these straight lines in it, AC and BD, cutting each other at some point E. And what we have set out to prove is that the rectangle contained by the segments of the one straight line will equal the rectangle contained by the segments of the other. What this looks like in our example is that the segments of the one straight line AC are AE and EC, and the segments of the other straight line BD will be BE and ED. And so we must prove that the rectangle contained by AE and EC equals the rectangle contained by BE and ED. Now, when these two straight lines, when these two chords cut each other, then they will either cut each other at the center or they will not cut each other at the center. Let's deal with the simpler case first, where AC and BD cut each other at the point E such that the point E is the center of the circle. And if this is so, then we know that AE, EC, BE, and ED must all be equal. They're all radii of the same circle. That's definition 115. And so it's naturally the case that the rectangle contained by AE and EC will equal the rectangle contained by BE and ED. Because all the straight lines are equal to each other, the rectangle AE times EC simply equals the rectangle AE times EC, and we know that AC is equal to BE, and we know that EC is equal to ED. We can swap these out by the property of magnitudes. We saw this plenty of times when we were dealing with book 2, so that we can say that the rectangle contained by AE and EC is equal to the rectangle contained by BE and ED. But it is not necessarily the case that these two chords, AE and BD, cut each other at the center of the circle. So let's deal with the much more common case that they don't. So we'll have two straight lines here, AC, BD, cutting each other at some point E, like so. And the point E is not the center of the circle. Now, if this is so, we begin by finding the center of the circle ABCD. We do this easily by proposition 3(1). And next, from this point F, we will draw the straight line FG perpendicular to AC, like so. So it falls on it at right angles. And similarly, we shall draw the straight line FH at right angles to BD, like so. We do this all by proposition 112 because the point F is not on the straight lines AC or BD. Now finally, we connect the straight lines FB, FC, and FE, like so. It's all just normal postulate 1. Now, because FG is coming from the center and falling upon a straight line not through the center, namely AC at right angles, we know that FG also bisects the straight line AC. So we can say that AC is equal to GC. This is proposition 3(3). Now, from the proposition after that one, proposition 3(4), we know that if two straight lines not through the center cut one another, they won't bisect each other. And that would tell us that the straight line AE is not equal to the straight line EC, which means that this straight line AC has been cut into equal and unequal segments, which means that we can leverage Prop 2(5), which tells us that if any straight line be cut into equal and unequal segments, the rectangle contained by the unequal segments plus the square on the straight line between the points of section will equal the square on the half. What that means for us here is that the rectangle contained by AE and EC plus the square on EG, right? Because the straight line AC is cut at the points G and E. So we know that the rectangle AE times EC plus EG squared will equal the square on the half. In this case, it'll equal GC squared. And by common notion 2, we can add the square on FG to both sides and say that the rectangle AE times EC plus EG squared plus GF squared equals GC squared plus GF squared. It's a simple common notion 2. Now, from 147, we see that we are dealing with two right-angled triangles, namely EFG, so that right-angled triangle right there. And we are also dealing with the right-angled triangle CFG, so that would be CFG would be that triangle right there. And proposition 147 tells us that the sum of the squares on the sides containing the right angle will equal the square subtending the right angle. And what that means for us here is that FE squared will equal EG squared plus GF squared. And similarly, FC squared will equal GC squared plus GF squared. It's all simple proposition 147. And so we can take this equation that we had up here and substitute some things out. We can substitute EG squared plus GF squared for simply FE squared, and we can substitute GC squared plus GF squared with FC squared. This is all simple properties of magnitude. And we also know that FC is equal to FB. They're both radii of the same circle. And so we can swap out FC squared for FB squared. Again, that's a property of magnitudes. We saw this plenty of times in book 2. Now, going through the same series of steps, that is steps 3 through 5, we can show that the rectangle BE times ED plus the square on FE will equal the square on FB. And now we have two things equal to FB squared, namely the rectangle AE times EC plus FE squared, and the rectangle BE times ED plus FE squared, which means by common notion 1, these two sums are equal to each other. And so we can say that the rectangle AE times EC plus FE squared will equal the rectangle BE times ED plus FE squared. And we notice that we have the same thing on both sides, FE squared, and so by common notion 3, we can take that away, and the remainders will also be equal. That's, again, common notion 3. And so we can say safely that the rectangle AE times EC will equal the rectangle BE times ED. This being what we have set out to prove, we are done with the proposition, therefore, etc. QED. I have nothing to add to this proposition, so I will simply move on to 3.36.